We are starting chapter 17, which is called probability models, but it deals with two special probability models. One of them is called geometric, which is what we're going to talk about today, and the other one is called binomial. So very important, and actually they're my favorites. Anyway, so starting off here with an example, suppose a basketball player's free throw percentage is 90%. Part A, what's the probability that he makes his first free throw on the third attempt? I have to be careful with saying these because it's like a tongue twister. So you think about what that means. So first of all, the probability of success, I'm going to call that P, equals 0.9. That's the probability that he makes it. So the probability that he makes his first free throw on the third attempt. So if you think about what that would mean, that means he misses the first one. Well, the probability of missing the first one is 0.1. He misses the second one, and he makes the third one. So you can kind of do a problem like this kind of intuitively. So if you multiply these, now I'm assuming that each time he goes to make a shot, that each trial is independent. So 0.9 times 0.1, well, you know 9 times 1 times 1 is 9. You got 3 decimal places, so you're going to end up with 0.009. So that would be the probability that the first free throw is on the third attempt. So then what's the probability he makes his first free throw on his fifth attempt? Well, yeah, I could write out the 0.1 times 0.1. He misses it 4 times, and the probability that he misses it is 0.1. So he would have missed it 4 times, and then he makes it. And so that probability, we're going to end up with 5 decimal points. 1, 2, 3, 4, and then the 9. So that would be the probability that he makes his first free throw on his fifth attempt. Then the next question, what's the probability that he makes his first free throw in his first 3 attempts? Now you got to think about, what does that mean? Well, that means that maybe he made it in the first attempt, or maybe he made it on the second attempt, or maybe he made it on the third attempt. Now I'm going to introduce some notations here and kind of go back to these. This one I'm going to call the probability that x equals 3. And that's going to represent the probability he made it on his third attempt. I'm going to call this one the probability that x equals 5. And that's going to represent that he made his first free throw on his fifth attempt. So then the probability he makes it in the first 3 could be the probability that he makes it on the first one, or, and we would add, because they're disjoint, the probability that he makes it on the second attempt, or the probability that he makes it on the third attempt. So then I'd have to calculate each one and add those together. Well, the probability he makes it on his first attempt is 0.9. Because he doesn't miss it at all, he just makes it. Plus, the probability he makes it on the second one, well, that means he misses the first and makes the second. Or, so I'm adding, he makes it on the third, which we already figured out here. So this is 0.9, this is 0.09, this is 0.009. So if you add those together, you're going to get 0.999, and that would be the probability that he makes it in his first 3 attempts. So again, pretty intuitive to do these. Then this next part D, I ask, what's the probability he makes his first free throw on his kth attempt? So now I'm introducing a variable in that case. So now all of a sudden I've got this, this definition here where P is the probability of success, and in our case it was 0.9. So instead of saying the probability that x equals 1 or 2 or 3, now I'm saying the probability that x equals k. That would be the kth attempt. Well, that would mean that the failure, if he made it on the kth attempt, that means k minus 1 times he missed it. And if P in our example was 0.9, I got the 1 by subtracting, or 0.1 by subtracting the 1 minus 0.9. So that's where this formula comes from. And this is actually called a geometric distribution. So again, this is a formula, but you hardly need the formula because it just kind of makes sense. So a geometric distribution is a type of Bernoulli trial. And the next one we're going to talk about, also from this chapter, the binomial distribution, the binomial model, is also a Bernoulli trial. So to be and this was named after a person, and I can't remember if it was John or James. There were two of them. I don't remember which one this was, but they were mathematicians who were very important in probability theory. And probability theory, a lot of it came about from gambling and wanting to know the odds for gambling. So, so anyway, that's where that comes from. So to be a Bernoulli trial, there can only be two outcomes, success or failure. The probability of P has to be the same for each trial, and you have to have independent events. So these three things have to be true in order to be Bernoulli. Now, a geometric distribution has to have these three things, and in addition to that, there's a fourth thing to be geometric. You have to be counting the number of trials until the first success. Now, if you look back at the wording of this problem, I kept talking about the first free throw. The first free throw, because that's the first success. And to be geometric, those are the clues you're going to look for to tell you that it would be geometric. So, if you remember when we had our, and we actually just talked about this in class yesterday, talking about a normal model, that the parameters for a normal model are the mean and standard deviation. And so when you write this is understood for the notation of a normal model. Well, for a geometric distribution, we use a G. That makes sense. And there's only one parameter, and that parameter is P, which is the probability of success. So when you're doing a problem and you recognize that it's a geometric distribution, you're going to want to put G, and then like the problem I just did, I would identify G with 0.9 being the parameter because that was what it was. So the geometric model answers the question, how many trials until the first success? You can calculate the mean of a geometric model, which would be 1 over P. So for example, if we wanted to know on average how many trials would he have to do to get his first free throw, you would just take 1 over 0.9, and which if you did that, so if we did it for our problem, then we would say mu sub x equals 1 over 0.9. You can think of this as, well, you can do it this way. Move the decimal point one place, you get 10/9. So that would be the average. Then the standard deviation, oh look, I would think I was going to answer that down here. Oh, there it is. So the standard deviation, you have a formula here, the square root of 1 minus P over P squared. If you check your yellow sheet, the formula sheet, I'm pretty sure those are on there. So I already talked about this one right here. If you plug in the value to get the standard deviation for our free throw problem, you get 0.3514. Okay, so those are formulas that you'll use for the mean and standard deviation of a geometric model. So I'm going to do a problem from the book. Sorry, didn't have this on the notes handout, so you might want to pause this and copy it down. And this is on page 398, number 8 in your textbook. Suppose a computer chip manufacturer rejects 2% of the chips produced because they fail pre-sale testing. What is the probability that the 5th chip you test is the first bad one you find? Now, when you think about the probability of success for this problem, the probability of success, a lot of times we think that means it has to be a good thing. Well, in this case, we're talking about the probability about rejecting that it's a defective chip. So the probability of success is 0.02. Before I actually address this as geometric, let's kind of go through and say, is it even Bernoulli? How many outcomes are there? Well, there's 2, because either it's good, a good chip, probability of that is 0.98, or it's bad. So those are only 2 outcomes. Is the probability P the same for each trial? We are assuming that it is, because based on what the problem tells us, we are assuming that it is. They reject 2% of the chips produced because they're defective. And are they independent events? Well, we don't have any reason to believe that they aren't, that each chip that was produced is independent of the others. So going with that, and then to make it geometric, are we looking for the first success? Yes, we are. So that would make this geometric with a parameter, the probability of success of 0.02. So then this says, what's the probability the fifth chip you test is the first bad one you find? So I'm going to write that as the probability that x equals 5. It happens on the fifth chip. Well, that means the first 4 were good. So 0.98 to the fourth power times 0.02. So we have 0.98 to the fourth times 0.02, and we get 0.0184. I tend to round to 4 decimal places. Okay, next part, the next problem says, what's the probability you find a bad one within the first 10 you examine? So I'm going to think about the notation. Now, I don't want to say x equals, because it could be the first trial or the second or the third or the fourth or the fifth. I'm going to go all the way up to 10. So I want the probability that x is less than or equal to 10. So what does that mean? That means the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3 plus ... plus the probability that x equals 10. So think about the amount of work that would take. I'd have to figure out each one of those and add them up. However, your calculator can do this for us. So I'm going to go back to this problem right here, and I want to show you on your calculator. If you go second and then distribution, and we've used normal CDF. Remember, we never used normal PDF. But I'm going to scroll down, and actually it probably would be easier to do the up arrow. But you can see all these different kinds of distributions. This is binomial. We're going to come back to that. Geometric. You've got geometric PDF and geometric CDF. These stand for probability density function and cumulative density function. So depending on the symbol, if it's equals, we're going to use PDF. So for this one, we're going to use geometric. Oh, I guess there's a, well, I guess I didn't do that right. I want it to be perfect for the video. So we have geometric PDF. So I'm going to choose that. And then it tells me to put in the value of P. So P is, we're going to do 5. Oh, wait, no, it's not. That was not right. 0.02. And the value of X, which is 5. So these are the arguments I'm putting into it, 0.02 and 5. However, it prompts you, unless you have an old style calculator. Look at the answer, 0.0184. So honestly, to do one like this, I can write it out. I can do it by hand about as fast as I can locate geometric PDF on there. So when it's equals, you would use PDF. Now for this one, we are accumulating. We were adding them up. So we are accumulating all these different values. So if you are looking to find this answer, you're going to go second distribution, use the up arrow key, and you go right to geometric because it's the bottom of the list. So we've got geometric CDF, and if we choose that, we put in the value of P and the value of X. So that was 0.02 and 10. And when we do that, we get 0.1829. And that's the answer, and that's a whole lot easier than calculating each one individually and adding them all up. So this is the way that you would want to do that. So in general, let me just make a note of this. If you are trying to figure out the probability that x equals k, you would use PDF. If you were going to find the probability that x is less than or equal to k, you would use CDF. You got to make sure that you know which one, okay? Remember, for normal, we never used PDF, but for geometric, sometimes we do if it's equals, unless you just use the formula. All right, so moving on. Part C. Now, if you look in your book, there is no part C. I made it up. So the question is, what's the probability it will take more than 20 chips to find the first bad one? So if I use a symbol for that, I want to know the probability that it would take more than 20 to find the first bad one. Okay, more than is strictly greater than. So I want the probability that x is greater than 20. So let's think about what that means. Well, that means it could be that x equals 21, or, so I would add, x might equal 22. Maybe that's when we find the first bad one. Or maybe it's x equals 23. Or maybe x equals 24. Or ... And the question is, where do you stop? Well, that's one thing about the geometric distribution is theoretically it could go on forever, because maybe it takes the 100th trial before we find the first bad one. So we have this kind of this idea that it could keep going, it never ends. But we need an answer, and there is an answer. So what you have to do instead of addressing this, remember that probabilities of the whole sample space have to add to 1. So what you're going to do in this case, if you want to know the probability that x is greater than 20, then you're going to do 1 minus the probability that x is less than or equal to 20. Now, you do have to be careful if this right here does not include the 20. So this one has to. All right, so keep that in mind. I'll show you another example in a minute. So this is easy now because we can do 1 minus, and we can go second distribution, geometric CDF, because it's less than or equal to, and type in a 20 for x. So that was 0.3324. And if I subtract that from 1, I'm going to get 0.6676, if I did that right. So that would be my probability that it would take more than 20 chips. Now, and I'm not even going to do this in context, but suppose I wanted to know the probability that x was greater than or equal to 25. Well, I can't do, CDF requires it to be less than or equal to. So if I were going to do this, subtract from 1, and I'm going to actually put here and then talk about why. This right here, if I had greater than or equal to 25, this included the 25. So when I do the complement, it can't include the 25. I can't include it in both places. So that's the reason why I had to drop the number down. The reason I didn't have to drop the number down here was because this was strictly greater than, not greater than or equal to. So I was not including the 20 in this part, so I had to include the 20 in this part. So be careful, because that can kind of trip you up. So I think, actually I was going to do one more thing, and this is number 10 on the same page. And the question was just, how many do you expect to check before finding a bad one? or a bad chip. So focusing on the word that it's talking about, expected value. So this is actually asking for a mu sub x, which if you look back at the formulas I gave you is 1 over p. So this would be 1 over 0.02. I would just move the decimal point 2 places here. So we get 100 over 2, which is 50 chips. So on average, we would expect to check 50 chips before we found our first bad one. So that is it for the geometric model. And so you should be able to do problems that I have assigned regarding this.